was electric flux. And what was the electric flux? This was E dot A. So similarly, we have magnetic flux, which is B dot A. So this is BA cos theta. So this is the magnetic flux, and this is very important in generating induced current or induced EMF. We can generate the induced EMF by changing the magnetic flux, right? So can you guys tell me that how many parameters are there on which this magnetic flux is dependent upon? How many parameters? How many parameters are there? Yes, magnetic flux is dependent upon how many parameters? So you have magnetic flux. This is dependent upon what? This is dependent upon magnetic field. This is dependent upon area of the cross section, and this is dependent upon the theta. So all these combinedly forms the magnetic flux, right? And what does Faraday's law say? That if I change this flux, then there would be an induced EMF, and how much that would be? So that would be minus n. Let's say I have number of n turns, and this d phi by dt. So by changing the flux, I can change the induced EMF, right? I can have this induced. Some EMF would be induced, and that would be equal to this change in flux. And there are three ways to change the flux, and those are the three things, right? So these things you guys have already learned, right? So I'll just quickly give a recap. And yeah, so this is the Faraday's law, right? This minus is the Lenz's law. So this tells about the direction of the EMF, right? What would be the polarity of this EMF? What is the positive terminal? What would be the negative terminal? So this is told by this EMF. And what would be the direction of the induced current? So this Lenz's law states that the direction of the current will try to oppose the change. So this is minus sign represents the opposition or the opposing force which is opposing the change of electric flux, right? Whatever by whatever means it is happening, if it is changing by changing the magnetic field, so this minus sign will try to create another current which will create another magnetic field which will try to oppose the change. So this is how this Lenz law works, right? It will try to oppose the change. So this is Faraday's law, and then from this EMF we can calculate the current, and from this current we can calculate the charge as well, right? So all these things will see, right? So this thing I have discussed that how can we change this magnetic flux? By changing magnetic field, by changing area, by changing angle, right? So and this Lenz law we have already discussed that if this n is approaching, then what should be the polarity or what should be the magnetic pole so that this change will be opposed, right? So these things we have already discussed or not discussed, but we will do this problem, right? So it is we can do this problem now, and after that I'll have my friend, and then after that, right? So we can do this question. In this question, magnetic flux is given. Magnetic flux is given, that is 10t square plus 20t. And they want you to calculate, and this is in milliwebers, right? So this is in milliwebers. And time is in seconds, the magnitude of current. So they want you to calculate the current, but they have given the resistance. The resistance is given, which is 2 ohm, right? So we can calculate the resistance, we can calculate the EMF using this flux, right? We can calculate this flux, which is, let's forget about the minus sign for now. This is d phi by dt. This is the EMF, and we know that what is the relation? Voltage is IR. So we can calculate this I, right? Let me write it in small letters. So this would be simply E by R. So E is d phi by dt, and then we have 1 by R. So this would be the current, right? And we have to find out the current at t equal to 5 seconds, and is in milliampere. So this is a very simple question, right? Let's do that. So let's first find out what is EMF. EMF is d phi by dt, which is 20t plus 20, right? And we have to find out this EMF at 5 seconds. So at 5 seconds, what would be this thing? This is the EMF at 5 seconds. This is 20 into 5 plus 20, which is 120, right? So this is the EMF, and we have the resistance, so we can calculate. And remember, this is in milliwebers, right? So we have to write it in webers. So this would be, right, into 10 to the power minus 3. So this is into 10 to the power minus webers. So this would be into 10 to the power minus 3 webers. We have to use the SI unit, so this would be in webers. I is simply E by R, so E is 120 into 10 to the power minus 3 divided by R, which is 2 ohms. So this is 60. So 60 into 10 to the power minus 3, and we have to write it in milliamperes. So this is 60 milliamperes. So this is 60, right? So this dash is 60, whatever this dash is, right? This would be 60. Is it clear, guys? This was a direct question. You guys please note it down, and I will be back in a moment. So I'll just have my iftar, and I'll be back in a moment. So you guys just note it down, and if you guys have any doubt, please tell. So I'll be back in a moment. Please give. Yes, hello guys. Yeah. So yeah, you have just joined, right? So we have just discussed that how we can create or how we can induce the EMF, right? And we can create the EMF by just changing the flux, right? And how we can change the flux? So there are three ways to change the flux, and those are by changing the magnetic field, by changing the area, by changing the theta. So because flux is BA cos theta, so we can change all these parameters and then we can create. So this is the first question that we have done. Now let us do another question and to understand. Right. Let's do another question. Right. So we'll do this question. So let's do this question. So you have a thin wire whose area is 3.5 and 10 to the power minus 3 and right meter square. So area is this, and it is placed perpendicular to the magnetic field. So area is perpendicular, so theta is right. So it is placed perpendicular. So its normal would be at zero angle with this magnetic field. So theta is 0 degree. Theta is 0 degree, and then you have this magnetic field which is changing. So this is 0.4 Tesla sine 0.5 pi t, right? So magnetic field is given. The field is in uniform in space. Then the net charge flowing through the loop during t equal to 0 second to t equal to 10 millisecond is closed, right? So we have to find out. The net charge. Net charge we have to find, right? So magnetic field is given and area is given, and we have to find out the charge. So what is the relation? Induced EMF is VA, right? d phi by dt, and this is equal to how much? So E is IR, and this is d phi by dt. So I is how much? I is dq by dt, right? So this dt and dt will cancel, and your charge would be simply d phi divided by r. So if I write it in delta, so this is delta q is delta phi by r. So this would be the charge which is net charge. So we have to only find out the change in magnetic flux. And they have given that we know that this is BA cos theta. So cos theta is 0, so this is only BA. And what is changing? What is fixed and what is changing in this thing? So this area is fixed. This remains constant. Only magnetic field is changing. So then delta phi would be simply, this would be area is fixed, so only delta B, right? So this net charge, this would be area by R and delta of B. So we have to find out only the change in magnetic field. A by R, change in magnetic field would be B final minus B initial. So this would be the net charge, and we have to find from t equal to 0 second to t equal to 10 milliseconds. So this we have to find, right? So what is this thing? What would be this thing? So B final at t equal to 10 milliseconds. How much is that? So this would be 0.4 Tesla, zero point 0.4 sine, and this is 0.5 pi, and t is how much? T is 10 millisecond, which is 10 into 10 to the power minus 3, right? So how much is this quantity? So this is 0.5 sine, and this is how much? 10 pi, and then into 10 to the power minus 3. So this is the sine angle, right? And then we have p at 0 seconds, right? P initial, that is t equal to 0 seconds. So how much is this? That is 0.4 sine, and then 10 pi, okay, 0.5 to 0.5, and then this is how much? So this is t is 0 second, right? So that is 0, so this would be how much? So this sine 0 is 0, so this would be 0. So we only need to find out this thing, right? How much is this thing? And we have to just put these values in here. So what we will get? So how much is 0.4 sine, and how much is 10 divided by 1000, right? Pi. So how much is this thing? So this is cancelled, and pi by 100. So how much is pi by 100? Right? How much is this quantity? So we can write this thing, right? We can write this thing as so this is okay, pi by 10. So if we write in this way, then it will become more clear, right? So how much is this pi by 100? 0.4, and sine. This is 3.14 divided by 100. So this is 0.4 sine of 0.0314. And how much is this thing? So this is in radians, right? So how much is this thing? Let me calculate. Sine of 0.031 radian, right? Radian, and sine of 0.031. 0.0314 sine. So this is 0.031, right? And multiplied by 0.3. This is 0.01. So this is a final magnetic field. Now we have to find out the net charge, and that is equal to A by R. So net charge would be how much? That is A by R, and then this magnetic field, which is 0.01. So area is how much? Area is given, which is 3.5 into 10 to the power minus 3. So 3.5 into 10 to the power minus 3 into 0.012 divided by resistance. How much is the resistance? So that is 10 ohm, right? So that is 10 ohm. So this will become how much? 3.5 into 3.5. So this is 0.0439 and into 10 to the power minus 3 divided by 10. So this is 0.0049 and into 10 to the power minus. So what is the answer? Okay. So this we can write as 0.44, right? So this is uh, this is 0.44 millicoulomb. So that would be the answer, right? There is a misprint in this thing. So this answer would be 0.4. The correct answer is 0.44 millicoulomb, right? This calculation is wrong. So the options are wrong and the correct answer is 0.4. Okay. But yeah, this is 10 to the power minus 3. Oops. This would be, okay, did I any mistake in here? So 3.5 into 10 to the power minus 3, right? And yeah, so this is 0.4 and then this is so 10 pi, right? 10 pi into 10 to the power minus 3, so pi by 100. So this is 3.14, so 0.0. So into, so this is correct, right? This is correct. So this answer should be not, so this should be 0.0044 milli. So this should be the answer, not this. So there are no options which are matching, but this is the correct. Okay, is it clear, everyone? Is it clear? If it is clear, please note this one down. So please note down this thing, right? Please note down this thing and then we'll do the next question. Yeah. Yeah, do you have any doubts?
No, sir. No, sir.
Okay, then please. Yeah, whenever you guys want me to scroll this screen, step. Oh, so I guess there is a mismatch. So this should be, yeah, if this is 10 second, right? So 0 second to 10 milli. Okay, so this one should be correct, right? I guess this is second. So if it is second, then the answers would be different, right? So this would be simply what, 5 pi, right? So yeah, then one moment. So this is 0.5. This divides by 10. So this is 5 pi, right? This is 5 pi. Let me correct this. This is 5 pi. Okay, so what is the value of 5 pi? So 5 pi is right. So this is how should we just 5 pi by 1000. So this would be 200. So pi by 200, right? And then oh, so, okay, is this the millisecond or Uh, yeah, if it is, it should be, I guess, second. This is second, right? Then what, what is this? Let's do this question in this way, right? Because we have this question. So let's do it in this. So this is pi by 200. How much is pi by 2.14 divided by 0.0157? And then we take sine. So 0.156. Okay. This would be 0.157, and then this is 0.0156, and then this is multiplied by 0.4. So this is 0.006 and 2. So this would reduce again, right? This would reduce again, but again we will not get the correct answer. So this is the correct answer, right? Into 3.5, so 0.0219. 0.0219. And then if we divide it by 10, so this is 0.002, right? 19 into 10 to the power, right? So this was the area. This is 3.5 into 10 to the power minus. So if they say, right, so if they say micro, then we can have this answer, right? But in milli, this would be, so this is this answer, right? If we are writing in milli or micro, then this would be 21. So if I'm writing 21, so this would be 10 to the power minus 1, 2, 3, 4, minus 7. So this would be the answer if I'm writing 20. But the powers are in here milli. So this is, yeah, this is wrong. This is wrong. So please correct this one. Please correct this one, guys. Yeah, how much did you guys note down in here? How much you guys have noted?
It's a little left.
Yeah, so please, okay, you have noted it. So then please note down this part. Yeah, please quickly note whenever everybody has noted it down, please. So then we will talk about EMF, right? And EMF meaning electromotive force, not the induced EMF. So motional EMF we are talking. Yeah, whenever you guys have noted, please tell. Yeah, noted everyone. Yes, guys, noted.
Yes, sir.
Okay, so now this part is done, right? So how do we get this magnetic flux Faraday's law? Now let us talk about the EM. So I will just discuss this briefly, right? So what do we do in EMF? So we have this length of the wire, and this length is moving with some velocity v. So it will create due to, because if this is moving in right hand side, right? So if this thing, if this length, this portion remains fixed, right? So this part remains constant. This part is fixed. Only this arm, this length is moving in this direction. So if you are moving in this direction, then this area will change. So this area will change, and due to change in area, you will get the motional EMF. So this is called the motional EMF, right? Because we are moving this length of the wire. So this is motional EMF, and this is equal to BL, right? And in vector form, this is written as minus B, and this is L cross B. So this is how we write it, right? And this is this is the EMF, motional EMF, and you can have right. So then you can write the current using this EMF, and you can also have this kind of thing that if you are rotating this rod in a circular then what is the motional EMF? So in that case, you have to remember that this is I 1 by 2 B omega L square, right? This is the magnetic field inside, and then this is the rod length, and then you're rotating it in circular direction. So then your EMF is half B omega L square, right? And this is the third case. And in the second case, what you're doing is that you have another motional EMF. So you're rotating this aperture. This area is fixed. This magnetic field is fixed. So you have this thing which is fixed. This thing is fixed, and uh, this uh, this working principle is used in AC generator, right? So this idea is used in AC generator wherever you have this aperture, and this is rotated. So if you rotate this aperture, so only theta is changing, and due to change in theta, you will have this EMF. So motional EMF is B omega sine omega t. So you will have three kinds of motion EMF, right? One is B omega sine omega t, and then in circular motion you have half B omega L square, right? And then you have BLV. So these are the three kinds of motional EMF that you have. These can be the three cases, right? And then you can calculate the current using this thing. So current would be simply E by R. So this thing we can easily calculate, right? Depending upon what are the things which are given. So if you are given the velocity, then we will use this thing. If you are given the rotation, angular velocity, then we would use this thing. And if you are given the omega again, but the aperture is rotating, then we will use this thing. So this is used in AC generator, right? When we'll talk about AC, then we'll see that how this is important, right? So we'll talk about this thing in AC as well. But these are the three forms of EMF, and current is simply E by R. So only this thing we have to remember. And now let us do some questions to understand these, right? So we will do this question, right? We have this question, and these questions are very simple, right? So if you think it properly, then this becomes very. Okay, so what is given in this question? So you have a square loop of side 20 centimeter and resistance 1 omega is moved towards right with a constant speed v naught. The right arm of the loop is uniform, right? And magnetic field of 5 Tesla. The field is perpendicular to the plane of the loop and going into it. The loop is connected to a network of resistance each of value 4 omega. What should be the right? What should be the value of V naught so that a steady current of 2 milliampere flows in the loop? So we have to move this V naught in such a way that we have a steady current of 2 milliampere. So current is given, right? Current is given, which is 2 milliampere, and the resistance of this circuit is also given. So we can find out what is the EMF which would be creating in this thing, right? So let's find out the effective resistance. So from this point to this point, PQ, this is in series and this is in series, right? So the effective diagram of this thing is this one. So we have PQ, which is 8 ohm, and then this is P, and then we have 8 ohm, and these are connected in parallel. So what is the effective resistance? Effective resistance would be simply 8 into 8 divided by 8 plus 8. So this is 64 by 16. So that is 4 ohm. So resistance we know, right? Magnetic field we know, current we know. So we know that how much would be the EMF. EMF is IR. So this is 2 milliampere. And then resistance is 4. So this is 8 into 10 to the power minus. And this EMF is related with this motional EMF, right? So this is BL V naught, which is the velocity. So E is 8 into 10 to the power minus 3. P is 5 Tesla. L is given 20 centimeter, right? And then, okay, and oh, so we have this 5 ohm resistance, right? So there would be a total R effective. So R effective would be 5, right? So the 4 and 5 ohm resistance plus the resistance of this square. So we have to, yes, we have to calculate the resistance of it as well, right? So what is the resistance of this thing? So the total resistance would be this thing plus 1, right? So R prime is 1 plus R effective, which is 5. So then what would be the current or what would be the EMF? So EMF would be IR, and this is how much? 2 milliampere, and then 5 ohm resistance. So this is 10 into 10 to the power minus. So this is the so this is related with BLV naught, and this is 10 into 10 to the power minus 3 equals to magnetic field is 5 Tesla, length is 20 centimeter, which is 20 into 10 to the power minus 2, and we have to find out this V naught. So V naught would be 10 into 10 to the power minus 3 divided by 5 into 20 into 10 to the power minus 2. So how much is this thing? So 10 into 10 to the power 2 divided by 5 into 20, and then this is right. So this 10 to the power 3. So this is 10 to the power 3, this is 10 to the power 3, cancels out. And then what do we have? So this is 1 by 100, and meter per second. This is 1 centimeter per second. This would be the velocity. Right. Is it clear, guys? Is it clear? So we have to also incorporate the internal resistance of this thing, loop. Then the total resistance, yeah, so we have to take care of this total 1 ohm resistance as well. So is it clear, guys? If it is clear, then quickly note this thing down. Quickly note it down and then we'll do the next question. And whenever you guys have completed noting it down, please. Yes, whenever you guys have noted, please tell me.
Road, sir.
Noted. Okay, so now let us do another question, right? And yes, let's do this. So in this one, what are the things which are given? So you are given a circular conducting coil of radius 1 meter is being heated by the change of magnetic field passing perpendicular to the plane. Right, so you have a circular coil and magnetic fields are passing through this circular coil. And these magnetic fields are changing like this. So magnetic field is changing, right? Magnetic field is changing, area is fixed. Area is circular. Area is fixed. This area remains constant. And because these are perpendicular, so the direction between the normal of this area vector, which is this normal, and magnetic field, that is 0. So theta is 0. So phi is simply BA, right? Cos 0 is 1, so phi is BA. And we have to find out the energy dissipated by the coil before the magnetic field. So energy, we have to find out the energy. And we know that energy is related with what? So that is I square RT, right? Or this is E square by RT. So we can use any formula, right? So we have to find out this EMF and then from this EMF, we can find out the energy, right? So we have to find out E. Time is also not given. So the energy dissipated by the coil before the magnetic field is switched off. So magnetic field is switched off means that magnetic field becomes zero, right? And this is the function of magnetic field. So this magnetic field is increasing or decreasing. What is, can you guys tell me? Is this magnetic field increasing or decreasing? Yeah. With time, is it
Decreasing.
yes? What did you say? Yeah, increasing,
Decreasing it is.
decreasing, right? So this is minus of t by 100. So this is decreasing. Means that at some point it will become zero. So when it will become zero? So if we put it equal to zero, p is zero. So what would be the time? These are constant, right? Let's say c by 100 Tesla. This is zero. This in the right hand side this goes and this becomes zero. So 1 equals to t by 100. So at t equal to 100 seconds, the magnetic field is zero. So we have to find out the energy at this time. But before we do that, we have to find out this E. So what is this E? This is simply d phi by dt. And we know that area is constant. So area is taken outside. This is d b by dt. So what is this area is 1 meter, right? So this is circular. So area would be pi r square. Area is pi r square. So this is pi. R is 1. So right. And then let's write it as 1 square. 1 square and then d by dt of this whole function 4 by pi 10 to the power minus 3 1 minus t by 100 and then yeah, that is delta. So this is constant, it will come outside, right? So pi into 4 by pi and 10 to the power minus 3 pi cancel d by dt of 1 minus t by 100. So 1 is a constant. So its differentiation would be right, and we have this minus sign as well. So let's write this minus sign. So this is minus, right? This is 1, so it will constant. It is a constant, and differentiation would be 0. So only this differentiation will survive. So we'll have minus, this minus again, and then we have 4 into 10 to the power minus 3. And this constant is outside, so 1 by 100, and then dt by dt. So that is 1. So this would be 4 into 10 to the power minus 5. This is the EMF, right? So this is the EMF, and then we have to find out, right? Then we have to find out the heat. That is E square R and E square by R and T. So E square is 4 into 4 and 10 to the power minus 10 divided by R is 2 micro ohms. So 2 into 10 to the power minus 6. And then we have time, which is 100. So how much is this thing? So we have 4, this thing is cancelled. We have 8 and then 10 to the power minus 10. This is minus 6. It goes in the numerator. This becomes plus 6. 6 plus 2. So that is how much? That is 8. So this is 8 into 10 to the power minus 2. And this is written in millijoules. So we will write it 80 into 10 to the power minus 3 joules. So this is 80 millijoules. So this would be 80, right? This is 80. So the answer would be 80. Is it clear, guys? Is it clear?
Yes, sir.
Yeah, then please note it down, right? Please note it down, and if I do any mistakes, please tell me. So, yeah, the answer should be 80 millijoules, right? But if I remember it correctly, the answer was different. Okay, let's see that. So radius is radius by GH. This is 2 micro, and then d5 by dt, 1 minus t by 100. This goes outside, pi cancels, 4 into 10 to the power minus 3, and this is minus 1 by 100. So this is correct, 4 into 10 to the power minus 5. Yeah, and then minus 10. So this is, yeah, this is okay. Yes, whenever you guys have noted it down, please tell. Whenever you guys have noted it. Yes, whenever you guys have noted it down, please tell. Yeah, whenever you guys have noted it down, please tell me.
Road side.
Done. Okay, so this completes this motional EMF, and then we have mutual and self-inductance, right? So you guys have learned, right? You guys have learned that we have self-inductance. So the current is flowing in this solenoid, and due to the induced EMF, right? So there would be some self-inductance. And we know that the flux is directly proportional to the current. So if we remove the proportionality, then we'll get this L, and this is called the self-inductance. And this is equal to this mu naught n square LA for solenoid, right? So just write this formula. This formula is only the important one. So just note down this formula for self-inductance, this formula for mutual inductance, right? So just note down these two things. Yeah, just note down these two things, and then we'll do a couple of questions. This is this, where n is the number of turns per unit length, right? So that is capital N divided by L. This is N by L. Yes, noted, guys. Only you have to note down these ones and this one and this one. Just only note down these two. Noted, guys. Yes, noted. This is the self-inductance, right? So this one is the self-inductance, and this is the mutual inductance. And if you put this thing in the medium, so if you put this thing in the medium, then this would be the self-inductance, right? So this mu naught is replaced by this mu, where this mu is the permeability of that medium. So you just change this mu naught to mu. So this is about self and mutual inductance, and this inductance is related with the energy, right? So we can find out the energy, and we can also find out what is the EMF for the inductor. So for inductor whose self-inductance is L, so the EMF is simply minus L di by dt. So this is the EMF of an inductor, right? And then the energy of this inductor U, that is simply half Li square. So this is the energy of the inductor. And you have to just remember, so only these two would be enough to solve all those things, right? So you have this self-inductance, mutual inductance, and then you have this EMF of the self-inductor and internal energy of this inductor. So these things you have to remember, and yeah. So now let's do some question, right? So let's do one question, and let's do this. Okay, so this is the question, right? And then this will complete your chapter. So you have a coil of inductance, right? L is given. This is 2 Henry. And then you have a negligible resistance is connected to a source of supply whose voltage is given by 3T. So voltage is 3T. If the voltage is applied when T equals to 0, then the energy is stored in the coil after 4 seconds. So you are given, right, voltage is given, and you know that how this voltage is related with the inductor. So you know that this V is simply L di by dt, right? And we can write because V is simply 3T, so this is L di by dt, and we can take this T the other side. So this is 3T dt, and then this is L di. So we can calculate what is the current at 4 seconds, right? From 0 to 4 seconds, how much the current is developed in the inductor. So that thing we can calculate, right? And let's calculate this thing. So this is integrated from 0 to 4, right? And let's say this is 0 to I. So how much is this? So we have, this is a 3T square by 2, and from 4 to 0, and then this is Li, right? So how much is this thing? Time is 4, so 3 into 4 into 4 by 2, and this is Li. So this is how much? 4 to the 8 and 24 divided by L, that is I. So how much is I? 24 divided by L they have given, that was 2 Henry. So this is 2, so this is 12. So I is 12 amperes. I we have calculated 12 ampere, and then using the I we can calculate the energy. Energy stored is simply half Li square. So this is half, L is 2. I we have just calculated. So these two cancels, and this is 144 joules. This would be the answer. Right, is it clear? So this was a two direct question, right? So if we just remember that what is the internal energy, what is the energy stored, and what is the EMF related with the inductor. So then we can do this question easily, right? So just if is it clear, guys? Do you guys have any doubt in this one? If there are no doubts, then please note down this part, right? Please note down this thing, and then we will do the. So this chapter is completed. We have talked about the Faraday's law. We have talked about the flux, magnetic flux, and how we can change the magnetic flux to generate the EMF, that is n d phi by dt. And then we have this Lenz's law, and then we have talked about that how many things we can change. We can change magnetic field, we can change flux itself, we can change the angle, or we can change the area. So doing all these things, we can have the EMF. And then we have talked about the motional EMF. So motional EMF is simply BLV. And then if we are rotating in circular motion, so that is half L omega square, or half omega L square, right? And then we have this aperture. Aperture is rotating, so that is B A omega sine. So all these things we have to. And then we have this inductor whose self-inductance is L. So that is mu naught n square pi L, right? And then you have the other thing which is mutual inductance, and that is mu naught n1, n2, and pi, and then n. So we have to just remember this. And then we have this energy stored in the inductor, which is half Li square, and then the EMF, which is L di by dt. So these things you have to remember. Yeah, whenever you guys have noted this thing, please tell. Whenever you guys have noted this. Yeah, whenever you guys have noted, please tell.
Noted, sir.
So now let us talk about AC, right? This chapter is done, so let's talk about. And we have already seen that how we can create this EMF. In AMI, we have seen that we have to rotate the aperture, and by rotating the aperture, we can create this EMF. So that will create this AC EMF, right? So from the AC generator, the voltage supply that you will get would be of this form. That is BA omega sine omega t. Area, angular velocity, and magnetic field, all these three quantities are constant. So we can, and they have the dimension of voltage. So we can write it E naught. And sine theta is a ratio, so that is dimensionless. So we can write the voltage supply in this form. And this would be the variation. So at 90 degree, the voltage would be maximum, at pi degree would be 0, and at 3 pi by 2, which is 270 degree, the voltage would be minimum. So voltage is fluctuating, right? It has an AC kind of behavior, or periodic kind of behavior, and this would be so the period would be 2 pi, right? In 2 pi, this thing will repeat its position. So this is how the electric or this voltage changes, and we have three parameters, right? One is that we have this peak voltage. So from this graph, you can see that this is the peak value, right? So this E naught is called the peak voltage. And then the second thing is the average EMF over a full cycle. So average EMF over a full cycle is 0. And then you have this RMS value, right? So average EMF in full cycle is 0. Average EMF in half cycle, that is 2 E naught by pi, and RMS is E naught by 2. So you guys just note down this thing. This would be important. So you guys have this supply, right? This is the supply of the voltage that you get from AC. So this is the supply voltage that you get, and these are the four kinds of voltage that you get. This is the supply. Quickly note down this part. This would be useful, right? Talk about this. Yeah, whenever, so just note down up to this point, right? Just note down up to this point, and this would be enough, right? No need to derive or just note down this. Yes, noted, guys. So this
Yes,
E
sir.
naught, this E naught is the peak voltage, right? Okay, and then in your CBSE course, you guys have learned about, right? Okay, so this is also important. So if you have two voltages supplied, like this one, right? So V1 sine omega t, V2 sine omega t, then RMS would be this thing. V square RMS would be square of these things, and current RMS would be also the same thing, right? So current RMS would be this thing. So you guys have to remember, right? If two voltage supply are you are getting two voltage supply, so this is V1 and V2 sine omega t. Then yeah, so you have to note down this thing as well. So please note down this one also. This is important. We'll do questions based on this one. So just note down these things, right? Yeah, note down these portions. So whenever you have the AC supply, just like let's say you have inductor or other things in resistance, right? In resistance, if you have this resistance, then from junction rule, I is I1 plus I2. But if you have the AC source, if you have this AC source, then this would not be I1 plus I2, right? If you have this AC source, then you have to apply this these things. So you have to apply the RMS values. Okay, just note down these portions and then we'll do a couple of questions to understand. So just note down this thing. And whenever you guys have noted, please tell. Yeah, whenever you have guys have noted it down, please tell. Yes, noted. Did you guys note it down? So always remember, whenever you have AC kind of source, right? And if there are parallel combination, these are different circuits. So let's say this is inductor, this is also inductor. Then you guys, you cannot write I equals to I1 plus I2. And you have to apply the RMS formula, right? So this would be the current. This would be the current. Noted, guys? Did you guys note it down? Noted?
Yes, sir.
Okay, so now to understand this thing, let's do one question, right? So let's quickly do one question. Yeah, so we have this question and we'll also talk about the next one also. Okay, so now let's first do this. So we have I, right, which is I1 sine omega t and plus I2 cos omega t. So you see that these are, what is I1 and I2? Can you guys tell me? What is I1? This is peak current, right? And what is I2? That is peak current as well. So we can calculate, we know the relation already that IRMS, right? IRMS is simply root of IRMS 1 square plus IRMS 2 square. So that is the IRMS, right? And if we calculate IRMS, so I1 RMS, that would be I1 by root, right? I2 RMS, that would be I2 by root 2. So what would be in here? So we have root of, this is I1 by root 2 whole square, and then plus I2 by root 2 whole square. So how much is this thing? This is I1 square by 2 plus I2 square by 2 over. So this is root of I1 square plus I2 square divided by 2. So this would be the option, right? So only this would be the option. Okay, is it clear, guys? Yeah, if it is clear, then quickly note it down and then we'll talk about the next question. Please note it down. Oh, who got disconnected? So two people got disconnected, right? Oh, Tarif got disconnected and then he's back. Yes, Iyad and Tarif, please note it down. Yes, note it, guys. Note it, guys. Yes, everyone, note it. Tarif and Iyad.
Yes, sir.
Okay, so now let's do this question, right? But before I do this question, let's understand this. So if I have a function, right? Let's say if I have a function which is I naught sine omega t. This is my function. Then if I calculate the IRMS, this would be I naught by root, right? But if I have a function which is, let's say I naught. So this is not fluctuating, right? This is not fluctuating. This is not sinusoidal. This is not periodic. This is a DC current. So for DC current, RMS value would be how much? What do I mean by RMS value? RMS value, what do I mean by that? So this is root mean square, right? So you take the root, then you take the mean, and then you square it. So this is called the RMS. But if you have a function which is not periodic, then IRMS would be same as this thing. So this would be same. Only if you have a periodic function, then only you will have IRMS, which is I naught by root 2. So in this question, we have two parts. This is a constant one, and this one is a periodic one. So we need to find out if we already know the relation that IRMS, this would be equal to IRMS 1 square plus I2 RMS square. But I2 RMS would be same. Oh, what is happening with, yeah. So I1 RMS, This is uh, simply, this is simply I naught, which is root 42 divided by root, I naught by root, right? So this is root of 42 by 2, which is root 21. And then I2 RMS, this would be simply 10. So we have this RMS, so this would be how much? Root of 20 square, root 21 square, and then we have this 100 square. So how much is this thing? So this is 21 plus 100. So this is 121. And how much is this? So this is 11, right? So I1 RMS, that is 11. So RMS value of this current is 11 amp. So dashed would be 11. Right? Is it clear? Yes, is it clear, guys? Oh, how many people are getting disconnected? So Tarif's network is fluctuating about. Yes, yeah, did you note down? Just note down this part, and if you have any doubts, please tell.
Okay, sir.
Noted already. Okay, good. So now we will talk about LCR circuit. In LCR circuit, in your CBSE course, you have individually already understood that we have resistive circuit. Resistive circuit doesn't have any phase difference with current and voltage. No phase difference between, so phi is 0. No phase difference between voltage and resistance, right? So this is also I naught sine omega t. And resistance is R. And then you have this inductive circuit. So for inductive circuit, this is the effective resistance, XL, which is called inductive reactance, and this is omega L. And then current is lagging behind 90 degree. So if you have this voltage supply, omega T, so this would be your current, right? This is the current for the case of inductive circuit. For the case of capacitive circuit, this would be the current, right? So these are the different circuits that you have. So in inductor, the phase difference is pi by 2. This is also pi by 2. This is leading, this is lagging behind. So current is leading in capacitive circuit, lagging behind in inductive circuit. And if we connect all those, so what is the power factor? Power factor is cos phi, and power dissipated is Vrms, Irms, cos phi. And then we have studied this LCR circuit, and using the phasor diagram, we know that we have an impedance which is simply R square plus not a root, but XC minus XL whole square. So this is the impedance, and then what would be the voltage? So peak voltage would be I naught, and then Z, and then Vrms would be how much? Irms, and then Z. So all these things we can write. So we can also write V. This would be VR square plus VC minus VL whole square, And then we can also write this phase angle, right? So what is this phase angle? So tan phi is VC minus VL divided by this base. And we can also write this is in XC minus XL divided by R. So these are the different scenarios, right? And we can also write cos phi. Cos phi is the power factor, right? So power factor would be how much? That would be simply base upon hypotenuse. So R by Z. So all these things we have studied already in LCR circuit. So all these things we have studied, right? The only thing that we have to remember is that if this is the current, right? Current is with the same phase as voltage, and this is lagging behind for inductor. This is leading ahead for capacitor. So this thing we have to, right? And you guys have just done this thing recently, so yeah, no need to note it down because you guys already know this. And then what are the other things that we have? Oh, so these two things are important. So we have resonant condition in which your Xc becomes XL. So this frequency is called the resonance condition, right? This is called the resonance condition, and this is related with inductance and capacitance, so 1 by root LC. And then we have this quality factor. So just note down these two things. The rest of the things you guys already know. So just note down, oh, again, Tarif has got disconnected. So just note down these two things, right? Just do note down these two things, and then we will talk about, we will do some questions based on this. Just quickly note it down. Yes, yeah, you note it down because Tarif, yeah, Tarif has, whenever you have noted it down, please tell. Yeah, whenever you have noted, yeah, please tell.
Noted.
Noted, yeah, your internet is also fluctuating, right? Okay, so let's do some questions, right? And yeah, this one is also very important, right? So this one is also important to understand. So what is open circuit and what is short circuit? When do we have to use these relations, right? So this is also important to understand. And let me just explain it to you, and then you just note it down. So short circuit is when the current is passing, but no resistance is provided. No resistance is provided, and then the current is, but the current is passing through this circuit. So that would be called short circuit. In short circuit, current is passing, current is passing, but there is no resistance, right? In open circuit, there is an infinite resistance, right? There is an infinite resistance, and current cannot pass through this circuit. So current cannot pass through this circuit, and this is called the open circuit. So no current will pass through the open circuit. I is zero, and I is not zero. So these things we have to remember. Okay. Now for the case of the capacitive circuit. So for the case of capacitive circuit, we know that this is the resistance of the capacitive circuit 1 by omega c. If your frequency is very large, so 1 by infinity, 1 by infinity, right? That would be, oh, what did I write? So 1 by infinity xc would be 0. So this is infinity, right? Omega is very large. Omega is infinity. 1 by infinity. 1 by infinity is 0. So resistance is 0. When is the resistance 0? That is called the short circuit. Resistance is 0. If omega is 0, if omega is 0, then 1 by 0, 1 by 0 is infinity. 1 by 0 is infinity, so resistance is infinite. Then that would be open circuit. Similarly, you have this inductive circuit. So in inductive circuit, the resistance is omega L. So this is omega L, and if omega is infinity, then resistance is infinity, so that is open circuit. If omega is small, then that would be resistance would be small, and this would be short circuit. So these are the things. Quickly note it down, guys. And yes, Tarif, can you hear me, Tarif? Hello, Tarif. Yes, Tarif, can you hear me? Hello, Tarif, can you hear me? Yes, Tarif. I guess your mic is. Oh, yes, Tarif, can you hear me? I guess there is a connectivity problem, right?
Yes, I can hear. Can you hear me?
Yes, I can hear. So you are getting disconnected again and again, right? What is happening to
Yes,
your
sir.
internet? So please note it down. Yeah, note it down, Tarif. Yeah, in Tarif's notebook, this would be already there, right? So this we have done just
Yes, sir.
yeah. So note it. Okay. Yeah. What about you? Note it already. Yes. Yeah. What about you?
Yes, sir.
Okay. So now based on this,
Okay.
yeah, we have already noted. So let's do one question, and then we will stop, right? So then let's so we have to just remember at high frequency. At a high frequency, what becomes open circuit? What becomes short circuit? Right. So this we have to only remember. And then this question becomes very simple. So we know that at high frequency, at omega in infinity, capacitor is short circuit, inductor is open circuit. Right. Inductor open, capacitor short at high frequency. So we have this capacitor. So capacitor is short circuited. So this is short circuit. Right. And then we have this resistance, and then this inductor is open circuit, right? So this is open circuit, and then this is short circuit, and then we have this 2 ohm. So this is short circuit, and then we have this thing, and then we have again short circuit. So this is the diagram, right? And V naught is given, which is 220. So what is this thing? 1 ohm, 1 ohm, right? And then this is 2 ohm, 2 ohm. So effective diagram. Oh, this is open circuit. So what is the effective diagram? Effective diagram is this one, and then we have this junction and this one and this one, right? and then we have this supply. So what is this thing? This is 1 ohm. This is 2 ohm, 2 ohm. So these are in parallel. So what would be the effective diagram? This would be this one, this one. So 1 ohm, and this is how much? 2 into 2 divided by 2 plus 2. So 4 by 4, so that is also 1 ohm, and we have this supply. So R effective is 2 ohm, right? And then we have to find out the effective impedance. Oh, so that is the resistance, right? So that would be 2. So this was the question. Is it clear, guys? You have to just remember the principle of open and closed circuit. So that is the only idea that we have to apply. Is it clear, guys? If it is clear, please note it down. And I will stop at here, right? So let me see how many questions do I have. And then in the next class, I will try to complete AC and EMI. And then on 4th, I will start, I have to check. So quickly note it down, guys. Quickly note it down, and then we'll do the next step. Or we'll stop. So only 2 people are here, so we'll stop. Where are the other people? They used to be, yeah. So where are the other people? There used to be 6 or 7 of us, right? Yes, yeah, I don't know. So they were preparing for their computer exams and they were supposed to join today, right? But their exam is on 8th of April. So I guess they will be after 4th of April, they will also be, right? Yeah, their exam will be, they had this computer exam. But you had also, you guys had also this computer exam. Yeah, note, have you guys noted it down?
Yes, sir, right.
Done. So we have other questions as well, right? So these questions we can do, but yeah, let's yeah, so we'll do all these questions next class. Yes, yes. In JEE, if there is a misprint in exam, they would give free marks, right? Yes, they will give you. They will give free marks for it, right? So even if you don't attempt it, right? Oh, no, no, no. You have to attempt, but yeah, because you don't know. If you don't know what is the correct answer, so yeah, they will give you free marks for the misprinted. Yes, yeah, they will give you the free marks. Okay, so we'll stop here, and in tomorrow's class, we'll try to complete this AC and EMI also have EMF, electromagnetic waves. So that part I also I will also try to complete. And then in the 5th on 4th of April, I will start ray optics and wave optics if I see if I can complete that. Yeah, we'll stop here, right? So okay, guys. Yeah, see you tomorrow, and Allah Hafiz, guys. Allah Hafiz, and